So I hope the presentation is visible to you.
Yes, sir, it is.
So basically, column means it is a member which is carrying direct axial load. In normal cases, we assume that it is actually taking up an axial load which causes compressive stresses that can control the design. So basically, the difference, major difference between, as Geetanjali was mentioning, the major difference between a column and a beam is that beams are basically flexural members, whereas columns are members, compression members. Okay, basically the compressive action will be predominant in the case of columns, whereas in the case of beams, flexural action is predominant, right? So basically we will be ensuring that these members, that is these columns, will not fail under compression, because the compression is the predominant thing in the case of a column. Okay, am I right? Is compression the predominant thing in the column? See, let's take a column like this. Say I have a column like this, a big column like this, and I am applying a load, and from the support also I will be getting some loads. So what type of action this will produce in this? It will be compression, right? Okay, but what I am doing is that I'm just increasing the length of this column. Okay, I am just increasing the length of this column like this, and I am decreasing the cross section. So you might have seen columns with small cross sections and having larger length. Okay, so please assume this to be straight. And in this also I am just applying a load. So will there be any difference in the behavior of this first case and second case?
Yeah, the second one will have more tendency to buckle.
Buckle. What do you mean by buckle?
Like it kind of bends.
It is?
It bends like along its length.
Okay, so basically in this case, in addition to compression, there will be compression. In addition to compression, we will be having some sort of the influence of bending here. Okay, we will be having this column bend like this or the other way, depending on the weakness in which direction it have. It will be bending to some sides, right? So basically, in this case, we will be having the effect of bending as well as compression. Okay, and one of you was actually, we usually say here also I have mentioned that the members carry direct axial loads. Okay, it is axial loads, but there is one thing that you should note. Say suppose we have a column like this, which will be the axis of this, and taking the side view. This is side view. So basically this is your vertical axis, and if I am taking the cross section, I will be say, let's take it as a square column. So I will be having a column like this. Okay, and I will be applying my load from this side. So in this case, the axis will be somewhere here. So please take, or I will draw it. So let this be the cross section, and we have the column going like this. Okay, and we have a central axis which is passing like this. Okay, so the normal thing is that by axial load means it should be perfectly applied at the exact center point, that is through the axis, and the load should be acting through the axis. Do you think that in practical case this is possible? So we will be having some beams and other things resting on this column. Do you believe that we will be having a purely axial load?
No,
No,
it can.
the chances of getting a pure axial load is very less. This load may be shifted to somewhere here or somewhere here, and this distance through which it is actually shifted, getting shifted, is represented by small letter e, and we call this as the eccentricity. Okay, so please understand that in practical case it is very difficult to get a pure axial load. In most of the things we will be having at least slight eccentricity. Okay, and when we design column, we will usually classify this design into two parts. In first thing, what we assume is that we will assume that, please note, we will assume that the load is perfectly axial, and we call such columns as axially loaded column. Okay, axially loaded columns. In that we will be having pure compression. The effect of bending will be very less in that. Okay, so when we have some sort of eccentricity in the column, there will be a tendency. So you can just visualize that instead of applying a load here, if I am applying it on this edge, there will be a tendency to, there will be a moment generated first of all, because we have this load acting here and we have a moment arm here. So basically there will be a moment generated, and as a result, there will be a tendency to get bent. So basically we have two types of things. One is axially loaded columns and another one is uh, columns with eccentric loading. Okay, so also in the first case where we have axially loaded column, we will not be considering the bending of the column. And in your course in DCS1, actually you have to deal with only columns which are axially loaded, and it is very simple thing. Anyway, in your next semester, you will be having a course called as DCS2, in which you will be learning about column by considering the bending also. Okay, so please have a brief idea on that. Now we will move into things. So basically columns are members carrying direct axial loads which cause compressive stresses that can control the design. In the case of beam, we were having flexural stresses which was predominant there, but here we have compressive stresses that controls the design. For we will be designing to ensure safety in compression. Okay. Now columns are members carrying axially load in the vertical direction, and we have one more thing called as another type of member which carries again axial load, but they will be, in most of the cases, they will be inclined. Okay, so such members which carry axial compressive loads in inclined direction is normally called as a strut. Okay, this thing we call as a strut, and when this strut is kept in a position, in the vertical position, we usually call them by the name column. Okay, so both of things are almost same, but we cannot call an inclined member which is carrying compressive force as column, but a strut which is kept in the vertical direction can be considered as a column also. Okay, so please understand the difference between these two, columns and strut. Again, both of them are members carrying compressive loads. Now, coming to the cross section. So, what all cross section we usually see for the case of columns? You might have seen circular columns, right? As pillars, circular columns. Then we have rectangular columns. Then we have square-shaped columns. Then we have hexagonal columns. And likewise, depending on the perspective of the architect, we will be having different cross sections provided for the columns. That is, as per the architect, the final design of the column, or what type of polygon we should take as the cross section, that will be mostly decided by the architect. Okay, now the basic thing is that concrete is strong in compression, so we know, but if we have some sort of bending, we are sure that there will be the effect of tension also, and we usually neglect the tensile strength of concrete in our analysis, right? In the case of assumptions made in the case of flexural design, we have seen that the tensile strength of concrete is assumed to be zero. So basically, we know that concrete is very good in compression. So basically, these are compression means members that can fail in compression. So concrete itself is enough. But the thing is that when we have the effect of buckling, that is when we have some sort of bending in that, what will happen? The tensile stress will come into picture. So in that case, there can be some sort of tensile force generated. Okay, so also there is another possibility that, say, when we have a column like this and we just compress it like this, there is a chance for getting these things bulged like this also. So in this case also, what will happen? There can be tensile stresses generated in this direction. So when we have this effect, okay, there can be tensile stresses, that tensile forces that generate in the perpendicular direction. So likewise, we may have some tensile stresses in the case of column. Also, predominantly in the case of bending, we will be having tensile fibers in this side and compressive fibers in this side, right? So there can be tensile stresses. So to take up this, we usually provide longitudinal steel, but we also know that steel is as good in taking compression as it is good in taking tension also. So steel is actually good in taking compression as well as tension. So what will happen is that even though concrete is very good in taking up compression, see, suppose we have a very large load, what will happen? The dimension of the concrete column required will be very high. So in order to reduce that, what we can do is that we can provide some longitudinal reinforcement inside this, so that this steel will help in taking some of the load. So that what will be the result? The result will be that we can reduce the cross section of concrete which is required to take up this compressive load. Okay, so that is another advantage of providing longitudinal steel in concrete. Okay, so longitudinal steel that resists tensile stresses caused by eccentricity also helps in carrying loads. Also, one more thing I would like to share is that, say you might have heard about lateral loads, say for example wind load, earthquake load. Likewise, we may be having some sort of lateral loads. So I'm just taking a column, say I'm taking it as 1D, and I am just fixing at the bottom point. Suppose I have a lateral load acting like this. What will happen to this column? This will have a tendency to get bended like this. So in this case also, we will be experiencing tension on this side, right? Tensile stresses will be automatically generated in this column also. So longitudinal steel resists tensile stresses caused by eccentricity or lateral load or whatever it may be. It will basically, longitudinal steel will take care of that. And if you see this, you can see that we have this is actually a picture taken from the actual site in which they are going to cast the slab. Normally, the beams coming, beams as well as some part of the column, beam column junction, this thing we call as beam column junction, will be casted along with the slabs itself. So this will be a single process in which they will be pouring the concrete inside the part of beams as well as these slabs, and it will be also filled in the beam column junctions also. Okay, and if you observe closely, you can see one thing. Say we have a beam which is going like this. So these are not based on your syllabus. I would like to share some more things from with you. That is why I am discussing about this. So if you observe here, we have a beam going in this direction as well as in this direction, and we have a column which is coming in the junction. So if you observe, the main reinforcements in the beams are actually bent and taken inside the column. You must always do it like this. You must not bend the longitudinal steel in a beam around the column. We must not allow, as an engineer, it is mentioned that we should not allow these reinforcement to go outside the column. It should always go inside the reinforcement which we provide in a column. So this is one thing that you have to note from this. And say basically, as we discussed, what are the functions of longitudinal reinforcement in column. So if we are talking in perspective of your university examination, we can expect two theory questions from this. One is explain the functions of longitudinal reinforcement in the column, and second one is explain the functions of transverse reinforcement, and more correctly explain the functions of ties in the column. We call the transverse reinforcement as ties, that we will look into. So in the following slides. Anyway, right now we will discuss about the functions of longitudinal reinforcement which we usually provide in column. So basically, these longitudinal, as we discussed, these longitudinal reinforcement are mainly provided to share the vertical compressive load, thereby reducing the overall size of the column. As we already explained, the vertical load will be shared by concrete as well as steel, so that we can have a smaller resulting cross section. Okay. So we can save a lot of money by reducing the cross section of our column. Then we have to resist tensile stresses caused in columns due to eccentric loading, moment, transverse loading. As I have mentioned, it is not only eccentric loading, it is due to eccentric loading, and due to the moment caused by any sort of cases. Then we have also the effect of transverse load that also can induce some tensile stresses in the column. So to take up all these things, we require some sort of longitudinal reinforcement to be provided in the column. Then we have to prevent sudden brittle failure of the column. We have already seen that we should not prefer brittle mode of failure. What is brittle mode of failure? The failure will be very sudden. Say normally the failure of concrete is brittle. We already know that it will fail at a fraction of few seconds. So if columns are actually failing like that, what will happen? We will not be getting any warnings, and we will not be able to evacuate the buildings. In the case of a failure, okay, I am talking in the case of a failure. So to prevent the brittle failure of the columns, what we usually do is that we will provide some sort of reinforcements inside the column, so that what will happen? When the tensile stresses exceeds the permitted value, or the compressive stresses exceed the permitted value of concrete, what will happen? It will be taken care by the steel, and the steel will start bending. It will show a lot of warnings for us. It will be failing in a ductile mode, so that when we observe these warnings, what we will do? We will just escape from the building so that the catastrophes can be avoided. So that is another important function of our longitudinal reinforcement which we provide inside the column. Then to reduce the effect of creep and shrinkage due to sustained loading. Normally, if we are not providing the longitudinal reinforcement, the effect of creep as well as shrinkage will be very high. And we already know what is creep and shrinkage. So when we provide the reinforcement, the effect of these two quantities will be reduced. That is another function of providing longitudinal reinforcement in a column. Any doubts in this? Okay. So, moving on to the next thing, functions of transverse reinforcement in column. So basically what we call the transverse reinforcement inside a column, I think in that figure we're having one transverse reinforcement. See, if you observe this, you can see that one reinforcement, small reinforcement is actually going like this. In between also we have a small reinforcement. What do you call that? It is called as, yes?
Tie.
Ties, yeah, exactly correct. We call those reinforcement as not stirrups. In the case of columns, we call them by the name ties. Okay, it is called as ties. And please don't mention when you go for some sort of interview or talking with some person, please don't mention the stirrups inside the column. Don't mention that. That is actually bad. We don't call these transverse reinforcement in a column as stirrups. We call them as ties. Okay, so basically right now what we are focusing is the function of transverse reinforcement in the columns, or in other words function of ties inside the column. So let's see what are the different functions of these things. To prevent longitudinal buckling of longitudinal reinforcement. So basically what will happen is that, say when we have a column like this, and when we apply this load, there will be a lot of reinforcement here. So basically these reinforcement will have a tendency to get buckled like this. Say this reinforcement will buckle in this direction and this will try to buckle in this direction. So what we will do is that we will provide ties like this. So what will happen when this thing have a tendency to get bent like this, these ties will hold it together. It will not allow to get buckled or bent in this shape. So that is one of the important function of our ties, to prevent the longitudinal buckling of longitudinal reinforcement. Then to resist diagonal tension caused due to transverse shear due to moment or transverse load. So as I already told, there can be a tendency for like this thing to get, when this compression is actually happening, there can be effect like this, and this will actually induce a tensile stress inside this. Say if you see the perpendicular direction, basically this is having a pinching like effect like this. So what will happen, there will be a effect of tensile, introduction of tensile stresses here. So if we have lateral ties going like this, these ties will actually take care of this tension, that is to resist the diagonal tension caused due to transverse shear. So this is basically a transverse shear that can be taken care with the help of our ties or longitudinal transverse reinforcement. Then to keep longitudinal bars in position during casting. Have you seen the casting of columns? So basically we will be erecting the casings on all the sides and we will be having the longitudinal bars. So when we pour the concrete inside this, what will happen? When this concrete comes and hit this longitudinal bars, it will have a tendency to get deformed. It will not be staying straight. Instead, it may get bented or it may be forming some other shapes. So to prevent this, what we will usually do is that we will be providing ties so that all the longitudinal reinforcement will remain in position. In addition to this, we will be also providing some spaces inside these castings, these casings, okay, so that it will keep the cover concrete in the required dimension. Okay, so we will be having some spaces. Spaces are normally spacer blocks. It is normally called as spacer blocks. Spaces we normally provide in the case of beams, slabs, as well as for all the casting, RCC casting, we provide spaces, spacer blocks, because we need to ensure that sufficient cover is there after the casting. So to keep longitudinal bars in position during casting also, we will be in need of these ties. Then to confine concrete. What do you mean by confined concrete? See, let me take one example. You will be having some sort of erasers with you, right? Rubber erasers with you. So let me draw this rubber. Say I have a rubber like this, and I am applying a compressive force on this. So what will happen to this rubber? It will have a tendency to get buckled like this. Am I right? It will have a tendency to get buckled like this. In the second case, what I am doing is that I am having the same eraser. I am going to apply the same load, but before this, I am taking a small cable or toy. Then what I am doing is that I am just completely wrapping this completely on through the periphery. I'm just keeping this toy tightly. So what will happen when you look from top? It will be this toy will be going all around this thing. It is actually what it is actually doing is that it is actually confining the material inside. That is the rubber is actually confined by tying it using this toy. Now if I am applying the same load, will it be having a behavior like this? No, it will not have a behavior like this. It will be much more stable. Similarly, inside the concrete columns also, see, this is the top view of a column. So basically, we will be having 4 longitudinal reinforcement, and to improve to provide a confinement so that we can reduce the buckling or we can make these things much more stable. What we do is that we will just provide ties like this. Sorry, we will be providing ties like this. So this will induce the confinement inside our columns, and this will help to keep or to provide a much more stable structure for us. Okay, so this is another important advantage of or function of a tie. So to provide confinement in concrete, to confine the concrete. Okay, so basically when you apply this load, the concrete inside this thing will be much more stable. It will be able to take much more load than a cross section which is not having any sort of ties. So if this was the same cross section without the ties, when we apply this load, this concrete will inside this inside the longitudinal reinforcement, the concrete will fail at a uh, much smaller load itself than that of a cross section which is having some confinements. Okay, that is another advantage of transverse reinforcement in column. Then to provide ductility to the column is again same thing which we have explained earlier. As we have more amount of steel, the thing will be more ductile. Then to prevent sudden brittle failure, same thing presented in a different manner to prevent sudden brittle failure of the column. So these are some of the functions of transverse reinforcements in column. And please note, this is one of the sure shot questions from your last module. We have only very small theory portions in this. So normally it is asked for 5 marks. Mostly they will be asking about explain the functions of longitudinal as well as transverse reinforcement in column. Or sometimes they will be specifically asking it for transverse reinforcement. This is more important. So explain the function of transverse reinforcement in column. Okay, so please note that these are the functions of longitudinal and transverse reinforcement in our columns. Then moving further, classification of columns. So basically based on the shapes, we usually classify the column. We have already seen that. We can classify it into circular columns, rectangular columns, square columns, or some sort of polygon. Okay. So based on that cross section, we can classify the columns into different types. Then based on the pattern in which we provide reinforcement inside a column, we can further classify the column. So let's see that. Columns with longitudinal steels and lateral ties. That is the normal column that we usually see. We have already seen. Yeah, here we have that. So if you see this column, you have the lateral ties here. Okay, we have the lateral ties here. So this is one type of column. Then what is the second classification then? Columns with longitudinal steels and spiral ties. So this is another. Normally in the case of circular columns, we will be having a ties provided. Sometimes we will be providing it in the perfect circular shape. Sometimes what we will do is that we will just spiral it. We will take a single reinforcement and we will be providing it as a spiral around the longitudinal reinforcement. Such type of columns are another second category, that is columns with longitudinal steels and spiral ties. Then we have one more classification, that is composite column. What do you mean by a composite column? Normally, sometimes what we will do is that we will be having the concrete, and sometimes we will be providing some sort of timber pieces on sides of that. Sometimes we will be providing steel sheets on sides of that. Basically, this column will be made up of a composite material. Such columns are usually being called by the name, or we bring in the classification as composite columns. Okay, that is another classification we provide for columns. Then we have braced and unbraced columns. What do you mean by braced columns? Have you heard the term braced columns? In analysis, have you came across these terms, braced columns and unbraced columns? You will be analyzing frames, right? No? Okay, anyway, we will see that. See, I think it's better to explain with this. Say this is a frame, you will be familiar with this. So basically, braced means we will be providing some struts like this. See, if you see, we have these columns going like this, and we will be providing a member connecting these columns, the nearby columns like this. So basically, this is called as diagonal bracing. So why we provide these bracings? Say you just assume we have a lateral load acting like this, and we don't have this bracing. That is our first case, and this is our second case. So which will be much more stable. So when we have bracings, what will happen to the overall frame is that it will be much more stable. So to increase the stability of the structure, we will usually provide bracings, especially when we have lateral loadings. So when there is an effect of lateral loading, we usually go with braced structures. Okay, and in the second figure, actually this figure, last figure actually shows a structure with bracings in both the diagonal direction. So this is braced in both these directions. So this will be much more stable than the first structure. Okay, so these are actually called as bracings, and these type of columns are called as braced columns. And if we don't have any sort of bracings, it is normally called as unbraced columns. So these are some of the classifications we usually provide for columns. Okay, now we have to discuss about a specific terminology called as effective length. Have you heard the term effective length? In MOS, you might have already learned this from Euler's equation. So you might have learned the Euler's equation, right?
Yes,
For
sir.
predicting the crippling load for the column. So in that case, if you remember the derivations, we usually derive the main equation. We actually derive only one equation. Okay, that is for the condition, end condition, that both these ends are hinged. Okay, we will be deriving only this condition. That is the reason why we have the effective length for a column with both ends hinged as one itself, one time the actual length. Okay, we will be selecting a factor. I don't know how you have represented. Was it lambda? Lambda times L. Have you taken it like that? And this lambda will be actually varying based on the end condition of our columns. So the thing that we have to understand is that effective length, the concept of effective length is when we derived the equation for Euler's from Euler's equation. So what we have done is that we have derived it for a case where we have hinge support on both ends, or this effective span was actually the distance between points having zero moment. So at this particular point, we know that when we have a hinge, the moment will be zero. Here also, when we have a hinge, the moment will be zero. So this the span or the length of the column was considered as the distance between the points having zero moments. So when we have different end conditions, say for example we have a fixed support at this point and we have another fixed support on the other point. So what will happen to this column? When this bends, it actually will not have any deflection at this particular point. After some part only it will be having deformation like this. So basically we have to actually find out the point where the bending moment is zero, and here also the bending moment is equal to zero, and at that the distance between these two particular points will be considered as the effective length. So in order to get this length, what we have to do, we have to actually multiply the actual length with, that is actual length means it is the distance between these two supports with some sort of factor. Okay, and these factors are actually given in your code. So based on the end condition, you have to select the required factor and multiply that and find the actual length of the column. That So that final length is actually called as your effective length. And the reason for this is Euler's equation is basically derived based on in the derivation. Actually, they have considered the length of the column as the distance between the points where we have zero moments. Okay, I hope you remember these things. Anyway, in page 94 of your IS 46 2000, it is given, that is how to find out the effective length for different cases. And I would like to point out one more thing there. Say it is in 94, page number 94. So here, if you see, we have effective length of compression members. So degree of end restraints of compression member. Then the pictorial representation is also given here. Then we have one thing called as theoretical value of effective length and recommended value of effective length. Okay. So again, effectively held in position and restrained against rotation in both ends. That means it cannot move. So on both the ends, they are effectively held in position. It cannot move and restrained against rotation. And there cannot be any sort of rotation. That means both the ends are fixed. In that case, what is the value of lambda? That is 0.5. So basically our effective length will be 0.5 times the total length. Okay, total length between the support. That will be the theoretical value of a column which have both the ends fixed. But when we go for the actual design, practical design, what we do is that we will the recommended value by the code is actually 0.65 times L. So this is based on experience, based on experimentation as well as experience. The recommended value for this case is actually 0.65 L. But if we are purely deriving things based on theoretical things, it is only coming around 0.5 times L. But actually recommended value is 0.65 L. Similarly, for different end conditions, we have different values of lambda. Say this will be one end fixed, another end hinged. In that case, we can go for 0.7 L if you are sticking on to the theoretical value, or 0.8 times L if you are going with the recommended value. Likewise, we have different conditions. So based on the, say, if you are speaking in terms of your examination, you just look into your question and you find out what is the end condition. Then you use the required value for your effective length. Okay, so this is something which you have to revise. That is regarding effective length. Then we have one thing called as short column and long column. Okay, so basically what is short column and what is long column? Long column will always normally fail in the case in buckling, whereas short column will undergo compression. See, basically we can easily visualize this. If we have a shorter column like this, a short member like this, and we are applying a load, what will happen? This cross section is very large. It will actually fail in compression, pure compression. It will just cripple, or it will just crush. It will be crushed and it will be failing. Say, instead of this, if we have a longer column, what will happen? Say a column like this. When we go on increasing this load, what will happen is that this will have some sort of bending also, and it will be failing in a mixed manner. There will be compression as well as there will be the effect of buckling. Okay, this thing we call as buckling. So there will be effect of buckling as well as compression, and finally it will be failing in that manner. And this type of column, this second type of columns is normally called as long columns, and the other one is normally called as short column. Now the thing is, for our calculation, how to check whether we have a short column or long column. So as per IS code, we have some provision for that. So what we have to do, we have to go with a ratio called as slenderness ratio. I hope you have heard these terms, slenderness ratio. It is a ratio of the effective length. So basically we have to calculate the effective length based on the support condition, and we have to find a ratio of effective length to the least lateral dimension. What do you mean by least lateral dimension? So when we have a column like this, suppose I have a rectangular cross section, and this is something like 100, and this is 150. So least of these two values, that is in this case it is 100. So ratio of effective length to least lateral dimension is normally called as slenderness ratio. So when we have a structure, see, we will take a actual structure. See, we have a column like this. Okay, so first thing is that we will just look in this direction. Sometimes what will happen is, suppose I have a roller here, and we have a provision for this column to move here. Slight movement is actually permitted. Okay, in this direction, this is our x direction. But when we take the other direction, this movement may not be provided, that is in the y direction, this in opposite perpendicular direction. Okay, this moment will not be permitted. So when we look from this side, that is LEX side, we will be having one L effective, because the condition here is we have this moment possible here. Okay, and here we have a fixed condition. So we have one end fixed, and another end we have this movement possible here. And on the other hand, when we look from the other side, the conditions are actually different. So basically what we have to do is that we have to ensure that in both these cases, that is the first one, LEX divided by the least of these two values. Okay, least of this dimension as well as this dimension. So if this is the least dimension, you substitute it as D. Okay, this ratio as well as LEY divided by D, both these quantities should be less than 12. In that case, we can classify it as a short column. Whereas if it is exceeding 12, then we can mention that as a long column. Okay, so this is how you have to classify that. So basically on both sides you have to see the end condition. Based on that you have to find out the effective length. Then you find out the slenderness ratio, and if the slenderness ratio is less than 12, that will be considered as a short column. On the other hand, if the slenderness ratio is greater than 12, that should be considered as a long column. Okay, so anyway, today it's time. So we will stop it here. Now we have to look onto the specifications regarding the design for column, as well as some of the assumptions that we make in limit state of collapse in compression. After that, we will move on to the actual design.